Okay, so good morning again. We will now look at maybe the another type of NMOS inverter. We have seen, just to review last week's subjects, we have seen that we can put this as the load element, but when we do that, output high is going to be limited. So it can only go up to VDD minus VTN of the load transistor. We can improve that by using another supply voltage, but then this requires a second supply, so that's not preferred. A simple solution is found by the process people. They said, maybe why not just use this as the depletion transistor, because if you do that, the threshold voltage is going to be negative, and then when you connect gate to source here, this is gate, this is source, then it's going to be always on because threshold voltage is negative. So therefore, when the input is 0, then no current is here, IDS is 0. But then, through this N minus channel, there's going to be resistance and no current through that resistance, and that node can be pulled up to VDD. Therefore, the output high becomes VDD. So that's the basic idea of doing this. And of course, this transistor, depletion transistor, is not available in a CMOS process. A dedicated process is used here. Dedicated process is developed to implement depletion load. Depletion NMOS. Okay, so depletion is not available in a CMOS process. We'll talk about the CMOS process later on. So in any case, we will be solving this now. When we solve this, we will come to maybe different methods. Again, we'll be maybe doing some analysis, standard analysis methods, and then we'll be doing graphical analysis later on also. So this ML transistor is like a standard transistor. Okay, so maybe I can draw here the curve. Maybe not here. Okay, maybe I should draw it here. So this is I ds of L, V ds of L characteristic. Drain is here, source here, gate is here. Okay, drain, source, gate. So here the transistor has such curves. We can draw this here. So this is the line where the gate to source is, I should do this here. V gate to source is less than V threshold of L, which is minus 2 volts. So, I mean, if we assume that device threshold voltage is minus 2 volts, because it should be negative, we know that. What does it mean? Why it's negative? Because here, in order to get zero current, we need to remove that N plus region by applying positive voltage here, okay, into this device. So therefore, threshold voltage is negative. So if we look at the other elements here, maybe we need to draw this. And this is V drain to source of L is equal to V gate to source of L minus V threshold of L graph. And here, we can draw maybe the other graph. So this is V gate to source is equal to minus 1 volt. This line is V gate to source of L is equal to 0 volt. So this is going to be our load line. Why? Because that's what it is. V gate to source is equal to 0 volt here. So that's the only curve that we are interested in for ML. Okay. So for this curve, when this is the case, Vin is less than this, we know that Mn is off. If Mn is off, then I ds of n is equal to 0, and I ds of L, which is equal to I ds of n, is going to be equal to 0. So we can see the output voltage. So this is what we are interested in finding. So how can we find that value from the graphic here? So we know that this is going to be the line, load line, okay? And here is the critical point. So this is the point. IDSL is equal to 0. So this is the solution, okay? Here IDS of L is equal to 0. If this is the case, we know that VGS of L is also equal to 0. So from that graphic, it's clear that VDS of L is also equal to 0. Okay, from the graphic, we can determine that, and that's the value, therefore, corresponding to here, because all these points belong to the case where we input less than the threshold of n, right? Because this is valid for all the values here. So this is another way of looking at the solution. So here we will be calling this region 1. In the region 1, Mn is off, What about ML? ML should be, this side is linear. Okay. So ML in linear mode. And the linear mode, what is the equation? IDS of L is equal to maybe Kn of L, V gate to source of L minus V threshold of L, V drain to source of L minus V drain to source of L square divided by 2. So the only solution here, we know that this is minus 2 volt, for example. So, you know, when you solve this thing, if this is equal to 0, if this is the case, then V drain to source of L is going to be equal to 0. So therefore, V out, which is equal to VDD minus V drain to source of L, is going to be equal to VDD. And that's going to be our output high case. So we can find this thing, the same thing, from equation or from the graphic, you know, wherever we want. Okay, I hope this is fine for the first region. So we'll come to the second region. So this is VDD, which is equal to V output high. This value is V threshold of N. 1. Okay. So if the voltage V in is slightly larger than the threshold voltage, let's call this thing 1 volt. What happens? If this value is slightly larger than VTN, MN starts turning on. Turning on. So there will be slight current. IDS of N. Therefore, there will be a slight voltage drop. Drop on VDS of L, because there is a resistance, remember? You know, there was a resistance in there. So, but V out will still be high enough so that MN remains in or stays in SAT. What was the condition for SAT? V drain to source of N is larger than V gate to source of N minus VTN. So this is slightly larger than VTN. slightly larger than ETN. So this is going to be small value. This is going to be still close to 5 volt. Therefore, the device is going to be in initially SAT. So therefore, there's going to be a slight decrease, okay, in the response, and until the point where the transistor goes into linear. Okay, so this is the second then case. For the second case, MN is in SAT, but ML in linear still. Okay. So, you know, after a point, I mean, there's going to maybe another case where ML goes to SAT, but you know, we are mostly interested in the next cycle where this will be like here, and when the input is VDD, which is equal to the output high, there's going to be the output low should occur, okay? Because then pulling down is going to be not that strong. Therefore, this is going to be the third case here. So there might be another case somewhere around here where ML changes its state. That, you know, that's not critical right now. So I guess this is now, you know, the response is obvious now here. So what is the, sorry, you know, we have to maybe look at the amount case. We drain the source of L, IDS of L, yeah, okay. Gate source, drain source, gate source. Okay. Maybe at some point, ML will go from linear to SAT. So somewhere around here. But in you know, basically here, this is the point where MN becomes linear. Okay. So if both of them are, if at some point, both of them are in SAT, then, you know, this line is going to be like this. It will be coming like that. And then this will be going like this. If both of them are in SAT, there's going to be, you know, maybe a sharp decrease. And then this will be the case. So if both Mn and Ml are in SAT. You know, a short while, this is going to be a sharp decrease is going to be happening. So we don't know. Those are the, you know, this will depend on the WR ratios of both transistors. This will be more clear in graphical analysis. Okay, so we can see this in graphical analysis. Okay. So that critical point, we can call this point, you know, this transition point as Vx. So I guess this is showing what happens after a certain time. Maybe we can draw it again. Here is VTN, and after that it goes like that. Maybe a short vertical thing here, but after that, this is going to be the case, and then this is Vx points. So yeah, so here, this region, Mn is in linear, maybe Ml in SAT. Okay, so this is VDD, this is VDD, we output low. I mean, again, this will act like an inverter, and then this will be our V. The input low is going to be here, the slope. And then here is going to be input high, but mostly that's, you know, finding those values are tedious and we don't care so much. So we look at the, eventually we look at the, maybe simulation results from the computer. So the definitions, I think we have already done. Maybe we can skip this slide. Okay. We can go to load line approach. So this is the line where drain to source of N is equal to V gate to source of N minus V threshold of N. Okay. And then we mentioned that the load line for the NMOS device is going to be, this is I drain to source of L, V drain to source of L. And this is it. Oops. Let's try to draw this again. This is V k to source of L is equal to 0 line. Okay, I should draw it like this one. Okay, so we know that this will be equal to Y drain to source of L, and V drain to source of N is equal to VDD minus V drain to source of L, right? I mean, this is V drain to source of L, so V out, which is equal to V drain to source of N, is like this. So here is this value, here is VDD minus DSL. And these are equal to each other, so that's good. Okay. So so how can we transpose this here? By the way, maybe this is not a very good one. This one is not very good one. Try to draw this a little bit better. Okay, so here for this graph, this point, when VDS of L is equal to 0, is here VDS of L is equal to 0 is this point. So this is VDD point. So if we increase this, no, this will be decreasing. So you know, the load line, in fact, is going to be something like this. Maybe I should draw it again. It will be, oops. I mean, this line is going to be transferred. No, not good. I'm not able to do this. Very good. Maybe this looks a little bit good. I don't know. Try to make this like this. I don't like it. I don't like it. I'm trying to do this so to show you that at some point maybe both transistors are going to be in SAT. Yeah. Okay, so here is maybe that line that I was telling you. Depends on the graph. Okay, so this is the line. Maybe I should draw this color. So here is the point where both transistors are going to be in SAT. So this is Okay, so this is going to be the load line. And so for different points of Vn, so here is Vn is less than V3 threshold of n, and that's the point here. So V threshold of n is the solution. And then this maybe is another point where the gate to source of n is equal to 2 volts. Let's say this is 1 volt. So for 2 volts, this is going to be the solution. So that's maybe is going to be like this. Slowly changing. And the corresponding output voltage is going to be this output voltage. Let's say VB. This is VB point. And then, there will be another point in the graphic. Maybe this is going to go to here. And then, it's going to be staying in there for a short while. And then, linear point. So depending on your solutions, this will be the gate to source of n is equal to 3 volts. So that's the 3 volt. I mean, this is not very good or linear, but I don't like the graphs here, but yeah, that's 2 volts. This is 1 volt. And then 3 volts is here. And then here, there's going to be a short region where both of them are going to be in SAT. And then it's going to be 4 volt and 5 volt. So when you come to solution points, let's say this is A, this is B, this is C, where C includes here, C, and then there's going to be D, E, okay? So let's say this is 4 volts, this is 5 volts, okay? So maybe this is going to be D, this is going to be E. So basically, that's how you find, and you see that after a while, there's going to be a small variation only in the output voltage. What is output voltage? This is V out. So V in V out graph is obtained like this. So I can maybe erase this part from the graphic. Okay, so notice here, this depends on the point, this point. This is the point where there might be a region where both Mn and Ml are in SAT. There might be, depending on the WR ratios of the transistors, this either happens or it doesn't happen. So for example, I'm going to draw this and then erase it later on. If your WR ratios goes like this, okay, such that this is the case, then of course here for this load, if the load line is like this one, we don't have that case, okay, because this is linear, and then the other one still will be linear when they cross each other. So just to let you know that, like that, MN, ML, and MN are not in SAT at the same time. Okay, so from the graphic, I mean, this is going to be visible. So this is useful. As you see here, the advantage of this here, depletion load allows us, enable us to get the output high as VDD. So that's a good one. Okay, a simple doping allows us this. So what about the fan out? You know, we know that this I gate is going to be equal to 0. So the fan out is not limited by the current again. Okay. The fan out is not limited by the IN prime current. Next, gate. As IN prime is here, I gate, which is equal to 0. Okay. But the fan out will be limited by the maximum switching frequency requirements. Okay, so we will have you know, this capacitance here. So here is going to be equivalent capacitance. We gate the source, or we equal, let's say. We equal capacitance. Sorry, why do I keep saying we equal? C equal. and C cool is going to be approximately equal to W times L times C oxide. Okay, so capacitance per area. So this is going to be equal to permittivity of free space times permittivity of silicon dioxide, relative permittivity of silicon dioxide divided by T oxide. So for each gate, so the C load is going to be N times C equivalent. Therefore, the timing will be affected from here. Charging time will depend on, and this charging time will depend on CL. Okay. This will be depending on the CL. So how fast you can do this is going to be T divided by 2. So how fast you can do is going to be limiting our device. This will be T divided by 2. And then F is going to be equal to 1 over T. So this is the fan out thing that we need to look at it. Okay, so we look at then up to now 3 different type of loads, and then the positive things and negative things about it. So just to summarize here, this for this circuit, this circuit. So here V output high is equal to VDD, which is good. V output low is not equal to 0. I mean, not good. And then you need to select RD is definitely not good. Okay, we don't like this RD. Occupies a lot of area. Here, there's no RD, so that's good, but the output high is equal to VDD minus V threshold of N2. Not so good. So the output low is not equal to 0, so not so good. This is another thing. Here, the output high can be VDD, can be. The output low is not equal to 0, but the bias, the second source, is not good. So this one here, the output high is equal to VDD, which is good. The output low is not equal to 0, so it's okay partially. A simple addition. To NMOS process. So it's okay. I mean, not expensive. Okay, so but in all these cases, we need to, design and select WR ratios of the transistors. For proper operation. Proper operation means so that the output low is less than VTN of VTN. Okay, so this is the case here. So when you select this one, of course, depending on the RD and VTN, so WR ratio of this one and then this value is going to be determining that V output low, and that V output low, select properly. So that the output low is less than the threshold of N transistor. Okay, so in all of these, select the WR ratio of this one and WR ratio of this one properly so that, output low is less than the threshold of N. Should be. Okay. So now, people started to think how to improve this, and then they come up with an idea. They said, why not use PMOS transistors and then, change the load with PMOS transistor. And we'll be seeing two cases here for the PMOS transistor. The one case is going to be just to use the PMOS transistor like a standard load. Okay. But the better one is going to be this one. This is going to be CMOS inverter. Okay. So this is an inverter in CMOS technology, but it's going to be not complementary operation-wise. So this will look like, this will be pseudo NMOS. So this will, operate like pseudo NMOS, where the output low is not going to be again 0. But this is going to be, if the input is connected to this VIN, so that gate, then this will be much, much better. Okay. So we will be looking at this and how this is going to be operating. Okay. Maybe I will give the break here, 10 minutes break, and then when we come back, we will continue. Okay. So record. Oops. Not sure. Okay. So we will look at inverter types that can be obtained where PMOS is used as the load device. Now we will first look at the case how PMOS can be used as a load, but then more interestingly, we will look at this one. Okay, so this is going to be the ultimate inverter that we can obtain with MOS technology. Okay, so here is going to be maybe how we can get this one, pseudo NMOS. I don't know if pseudo NMOS is talked later on. Let me look at the slides. Conception, power consumption. Okay. So before we start to CMOS inverter, we can look at this one, pseudo NMOS. And pseudo NMOS device, it would be good to have one extra slide here. We can obtain its graphic from maybe, again, input output characteristic from the graphical analysis. Let's do that here. Okay, so I'm going to do it here. Okay, pseudo so NMOS inverter, where PMOS is used as load. Okay, so let's just do quickly the graphical analysis for this purpose. If we call this thing again VDS of N and IDS of N, you know how the graphic and load line goes like this. So, this is the line where Vin is less than Vtn. And this is the line where we get the source of N, which is equal to Vin, which is equal to 2 volts. And then this is going to be 3 volts. This is going to be maybe 4 volts. And then it's going to be 5 volts. So that's how the currents are determined. Okay. So for the PMOS device, maybe I should use a different color for the PMOS. For the PMOS, this is the source to drain of P, I source to drain of P, and the graphics again are similar, where this one is maybe this is the source to gate is less than the threshold of P line. And then source to gate, this is going to be maybe like this. Okay, and this one is maybe I'll do this a little bit. PMOS has maybe smaller currents, as you know, because of the MOS transistor. Mu P is smaller. So this is 2, 3, 4, and 5 volts. So in this circuit, if this is ground, this is VDD, this is Vin, and this is Vout. Here is the source, Here is drain and gate. This is drain, source, and gate. Okay, so here, source to gate voltage is fixed. We source to gate of PMOS transistors 5 volts. So this is the line then. So this will be our load line. And this, since this one is equal to VDD minus this is equal to VDD minus the source of your P, and this one is equal to V out. We can, put that load line here. Again, the similar way, this point, which is 0, here is going to be 0, so that corresponds to this point here. And then, when we draw this, this will look like this one. So this is the load line. So any point crossing is going to be a solution. Okay, as you see here, then we can get this for this device. Input output graphics like this up to VTN. It's going to be VDD. Why? Because here is VDD. So when input is less than V threshold of N, this is the corresponding point A. So this is going to be B, this is going to be C, this is going to be D, and E points. So A point is VDD. So this whole thing is A. And then for 2 volt, 3 volt, 4 volt, and 5 volt, it goes like this. So first, maybe this is close to 5 volt. So this is going to be B. And then it's going to be again close to maybe 4 volts or so, like here. But then it drops very quickly. So maybe goes to here and then here, okay? So depending on that graph, this will continue like this, B, C, D, and E, okay? As you see here, maybe it would be better to make this like this, okay? So this is weaker PMOS. That means WL ratio P is smaller. Okay, so if it is weaker, then your graphic is going to be more like this. It will come like this. It will go like that, okay? So, so this will reach to lower voltages here. Okay, so but this will operate like what we know before, and this will be corresponding to the output low, or this will be maybe another the output low for different cases. So I mean, this is not much different than the other devices. The response will look like depletion load NMOS. Therefore, it is called pseudo NMOS structure topology. Okay, pseudo NMOS. But the more interesting thing is to connect the PMOS like this. This is going to be much better. And we'll see why it's going to be much better, I guess, in the coming slides, because if you do that, then this looks like, you have a device and switch, and then this is VN. So if VN is high, then this one is on, this NMOS is on, and the other one is off. And output is going to be switched to ground. If VN is VDD, then this switch is going to be on, and output is connected to Vout. So that's the CMOS inverter idea. Okay. So we can look at the CMOS inverter and find and determine the voltages and output voltage for extreme cases, and also we can look at this for the other cases. So what happens if the input is lower than VTN? Now, if the input is lower than VTN, so that's this point, so VTN point. Okay, so that's the case one. So if the input is less than VTN, then we know that MN is off. If this is the case, I drain to source of N is equal to 0. That's for sure. What about MP? If the input, so let's look at the case where input is 0, okay? So 0 is the same thing. So we don't know what is empty, but we know that I source to drain of P is equal to 0, because this is source, this is drain, this is drain, this is source, for the PMOS. So what about we source the gate of, let's say, P. So if Vn is equal to 0, we source the gate of P is going to be equal to what? VDD minus Vn. So it's going to be VDD. So we source the gate of P is VDD that is larger than V threshold of P. If this is the case, MP is on. So it can be either sat or linear. You know, sat means I source to drain of P is equal to Kp divided by 2V source to gate of P minus VTP square. But this cannot be 0 because this is 5 volt. Inside is minus 1 volt. So, but we know that, you know, the circuit forces this to be 0. So therefore, this cannot be the case. So it should be in linear. So MP should be in linear. If MP is linear, then what is the current relationship? I source to drain of P is equal to Kp V source to gate of P minus V threshold of P V source to gate of P, no, sorry, V source to drain of P minus V source to drain of P squared divided by 2. Okay, so if you make this equal to 0, then the solution tells you that if that's the case, the solution is that this happens to be 0 when V source to drain of P is equal to 0. Because this is 0, this is 0, then that's a solution. The other solution is not going to be possible. So if V source to drain of P is equal to 0, V out, which is equal to, this is V source to drain of P, VDD minus V source to drain of P is going to be equal to, this is 0, VDD, V out, which is going to be output high. Woo, great. So output reaches to VDD. Perfect. That's one extreme. Okay. I hope this is clear. You know, we could find this value also from the graphical analysis. When Vin is equal to 0, it looks like this circuit. Vin is equal to 0, it looks like this is 0. And then here, we also found out the response as here, VDD. Same thing. So we already found that before, but you know, this is another way of looking at this. So let's throw this here. This is VTN. And then up to here, this will look like VDD. So let's look at another maybe extreme. So this one, Let's call this thing 1. Case 2. For case 2, I'm going to look at first V in equal to VDD. In fact, when V in is equal to VDD, remember this is source, gate, and drain. We source the gate of P is going to be equal to 0 volt. So 0 volt is less than VTP. So this is -1, remember, -1 volt. So if this is the case, then MP is off. If MP is off, I source the drain, this current of P is going to be equal to 0. So this current forces I drain to source of N to be 0. Okay. So I drain to source of N is equal to 0. Circuit forces. Okay. So we are talking about this is 2 volt, 3 volt, 4 volt, and 5 volt. We are talking about this one. Vn is equal to VDD point. So, so what? If that's the case, how can we find the value of VDS, which is V out, VDS of N? Okay. So let's look at the case here. So here, V gate the source of N is equal to V in, which is equal to VDD. So Mn is on. Okay. So with the same logic, Mn is on, but the current is 0. That means, so Mn should be in linear mode. Okay. So this should be in linear. And then if you write the linear equation, I drain to source of N is equal to Kn. We source to gate of N minus Vtn times V drain to source of N minus V drain to source of N divided by 2 square. So the only solution is that we drain to source, this should be equal to 0. So we drain to source of N is equal to 0. Great. So this is our solution point. This is our solution point. So as long as when V in is between VDD and VDD minus VTP, then V out is going to be equal to 0 volts. So not only here, but all this region is going to be 0. Until when? This point. What is this point? VDD minus VTP. So, I mean, notice that V in is equal to 0. V out is equal to VDD. That's V output high. V in is equal to VDD. V out is equal to 0. That's V output low. So V output low is 0. Whoa. That's great. So voltage swing between rail to rail. Okay, so which rail? VDD to ground rail. Is that okay? Is that clear? So we could look at this from another perspective. You know, we could find the same value. If the PMOS is off, so let's call this thing 2, region 2. I mean, I could look at from the graphical analysis. This is I drain to source of N, V drain to source of N, and this is my load line here. V gate to source of N is equal to 5 volts. So we are here, and the current is 0. So this is telling me that if IDS is equal to 0, N, then VDS of N is also equal to 0, which is equal to V out. So I can also find that from this graphical analysis. Why IDS of N is equal to 0? Because IDS of P is equal to 0, because we are here 5 volt applied to the gate or to the input. So there are 2 ways to determine that. So let's just draw these again. Maybe like, you know, 1 volt, 2 volt, 3 volt, 4 volt, and 5 volt. Okay, so let's draw this. This is one region. The other region is here. This is VDD. This one is 0 volt. Not low. Not high. Okay, so then what is the third region? Now, there is an interesting region that we should pay attention to. So this is region 2, this is region 1. The third region is where the both transistors are in SAT. Okay. So this is a very interesting region. So we know that, Mn is in SAT if V drain to source of N is larger than V gate to source of N minus VTN. Okay. So VDS of N is this, which is equal to V out. And V gate to source of N is V in. So if V out is larger than V in minus VTN, then Mn is in SAT. So can we transfer this to our graphic? If the input is 0, it's here. Output is minus VTN. If the input is VTN, and output is this. So I can draw a line here. Okay. And then this is minus VTN. That's VTN. And if V out is larger than this, then Mn is SAT. SAT region. Okay. Can we determine the region where MP is SAT? MP is larger than V source to gate of P minus VTP. Source to gate drain is this one, V source to drain of P. V source to gate of P is this voltage. So what is their relationship with V in and V out? This one is equal to VDD minus V out. This one, VDD minus V in. Okay. So if I rearrange this, the graphic will be looking like this. If V out is less than V in plus VTP, then MP is going to be in SAT. So can I draw that in the graph? Yes. If input is 0, going to be VTP here. Another line is here, minus VTP. So if I draw this line, maybe not very good here, but here is going to be where MP sat. Here, MP linear. So they should be in parallel. Maybe my drawing is not very parallel. Maybe even this should be a little bit above. Even more here. Yeah, to the scale. Even it should be even more up. But there is a region where both transistors are in SAT. Okay, so that's the critical thing. Let's call it like 3. Where both MN and MP are in SAT. So what happens if they are both in SAT? If they are both in SAT, you know that I drain to source of N should be equal to I source to drain of P. So you can write the equations. I don't have much space to write, but maybe I should try to do it here. I'll do it here. I drain to source of N in SAT equation is like this: Kn divided by 2 V gate to source of N minus V threshold of N square. Okay. I source to drain of P is equal to Kn of P, or let's call it Kp, divided by V source to gate of P minus VTP square. Okay, so you know that this is equal to Vn. This one is equal to VDD minus Vn. And then we know that they're equal to each other. So if you solve this, you'll find a value of Vn. And that value of Vn is going to be equal to I need to look at this value, normal equation. Value of Vn will be VDD minus VTP plus VTN times square root of KN divided by KP divided by 1 plus Kn divided by Kp. Okay. This is a very interesting result. That's only one point. Okay. A specific case of this is, let's say Vtn is equal to Vtp and Kn somehow is equal to Kp. And we can arrange that with WR ratios. Then this interesting V endpoint is going to be equal to VDD divided by 2. Right? Because this will cancel this one. This is going to be 1. This is going to be 1. VDD divided by 2. So VDD at this VDD divided by 2 I guess my slopes are not so good, so we don't see this nicely, but there's going to be only one solution. So this will be region 3. Let me do this. Let me erase this and draw it again. It will look like this. Is that clear? So, I mean, this will be very sharp. In fact, if we include, these 1 plus lambda VDS, maybe that's not going to be that sharp, but in any case, it's going to be very sharp. So the rest of the circuit connection can be made easily. Maybe I should select a different color for that. No, maybe I should select something different. I don't know. This is it. So the response will be like this. Okay, it's not very good looking. But the slopes are going to be here 0. Slope should be 0. So I told you that, right? I mean, this should be maybe, the output V out according to the scale. If you do it scale properly, this is going to be V out. So this is going to be V out is equal to 0. So therefore, the curve is going to be like this. Very nice looking curve. Okay, so this will look like this. Slope. Okay. So this separation is going to be 1.5 volt. This is going to be 1.5 volt also. Very symmetric device. So I think I should stop here. But the nice thing is that V output low is equal to 0, V output high is equal to 0, and then I source to drain, for both cases is going to be equal to 0 when output is low, and I source to drain of P is going to be equal to 0 when output is high. Okay, so static power dissipation is 0. Okay, and this is the beauty of the CMOS inverter, and I think we will continue with this circuits drawing and see the advantage of the CMOS inverter. So that's going to be the cases. Any questions?